This is 2.6 day 1. This is the assignment here. Alright, domain. We've talked about domain in the past. Domain is basically all the x values that are usable. Now you can see here that when we have a fraction, we do not want any values where the denominator is 0. So if we put a 5 here, we'd have 5 take away 5, which gives me a denominator of 0, which is what I don't want. Now you can calculate that if you don't see that instinctually by simply saying, hey, I don't want this whole denominator to be 0, so that is not equal to 0. And which means that, hey, your x should not be equal to 5. And you can write that in interval notation. So basically our domain is everything except for 5. Here, you can either factor this into x plus 5 times x minus 5 and set each of those equal to 0 and figure out what you don't use, or you can solve the long way, set this whole thing not equal to 0 and solve that way, thus giving you, hey, I don't want positive or negative 0. Writing your answer in interval notation would look like this, because again, you want everything except for those two values, so you'd have 3 sections in your notation for your domain. The final example is x squared plus 25 in the denominator, and this is not factorable, so the only thing we can do to find the x values we don't want is to say, hey, I don't want this to equal 0, and then solve that way. Turns out we get plus or minus 5i, and those are complex numbers. Now, complex numbers don't show up on a real number graph, so to say that we want to exclude them doesn't even make any sense, because they're not real numbers. So basically, on this graph, since there are no real numbers that we want to take away, we simply say, okay, then all real numbers exist, and they're valid. So the domain is all real numbers, from negative infinity to positive infinity. Vertical asymptotes. Okay, vertical asymptotes are basically places where x does not exist. So when we're talking about the domain, we've already done a lot of that. We've already basically said these are the things where places where x cannot exist. So all you basically do is you look at the denominator of your original function. Even if it simplifies down to be something simpler, whatever the original function they give you is, that is what you need to think about in terms of excluding things. So I would say, even though we simplified it all the way down to x minus 2, we still have to go back to the original and say, hey, I cannot use negative 5 here. So therefore, our final graph would be looking like this line, except for there would be a hole at negative 5, because the original function looked like this, not like that. Same thing here, x squared minus 9 can be factored into those two things, and you would see on the graph that it would skip over 3 and negative 3. You wouldn't have any x values at those two places if I graphed this whole function. Okay, vertical asymptotes, or just little holes in the graph, come from what we just did, looking at the denominator and seeing what we would have to exclude, because then that would make that number, that whole thing, a 0. Here I took the denominator, set it equal to 0, not equal to 0, and found that I do not want either plus 1 or minus 1. So everything except for plus or minus 1 works on that one. Here, even though I'm canceling, I'm simplifying and canceling my expression to make it a simpler fraction, I still, again, have to use kind of my original things before I cancel in the denominator, my original factors, to determine what x values I don't want in my domain. So it turns out the domain here and here are the same, even though there was a cancellation here. That's really important to know. The rest of these, again, just as I did with example 3, here the denominator, once you say, hey, I don't want that to be 0 when you solve, it only gives you complex number answers, plus or minus I. So in this case, you don't have any exclusions from the domain, and you have all real numbers. One more example of canceling. Even when you cancel, you still have to go back to the original function and see what you do not want to be equal to 0. In this case, x minus 2 you don't want to be 0, so x equals 2 cannot be part of the final graph, even though we simplified it to this. And actually, it turns out that you get this line, there's just a hole at the x value where that would be a 2. I'm going to skip over this page. All right. Now, horizontal asymptotes are basically values where y doesn't have a counterpart. So they're kind of like horizontal lines where the graph doesn't cross it. The way that we find this is we look at the coefficients of our leading terms. So we look at the highest power on the top and the bottom, and we look at the numbers in front, and that tells us what kinds of horizontal asymptotes we're going to have, if we have any. So if the top coefficient is smaller than the bottom, then we have a horizontal asymptote that is basically the x-axis, y equals 0. If the top coefficient is equal to the bottom coefficient, then we have a line at y equals the fraction of those two numbers. And if n is higher, we either have what's called slant asymptote, or more than 1 degree higher, then it's going to be a curve. But this last one, the curve, is not covered in this pre-calculus textbook. Now I'll show you how to find each one of these three. Find the horizontal or slant asymptote. Well, basically, I'm looking at these two. I've got a second degree here and a second degree here, so these are my two leading terms. Now, since these are equal, since this power 2 is equal to this power 2, that means we have a horizontal asymptote at y equals the fraction of those leading coefficients, which would be 9 divided by 3, which is 3. So there's a line in this graph at y equals 3 where the graph does not cross through. That's a horizontal asymptote. Here is my leading term on the top, and here is my leading term on the bottom, and that means the ones with the highest power. So here, this is a first degree, and this is a second degree. So you can see the top power is less than the bottom power. That's n is less than m from the previous page. That means that we simply have y equals 0 as our horizontal asymptote. And then finally, this last one, you can see that this power here is a 2, and this power here is a 1. So this is higher than the denominator, which means that we do not have a horizontal asymptote. It's not horizontal. Now, I'll show you how to find a slant one in just a second. But there's a section in the book that simply asks you to find horizontal ones. So if this is greater in power on the top and the bottom, simply say no or none. No horizontal asymptote. Okay. Again here, there is no horizontal asymptote because this is a third degree and that's a second degree. So this would be nor horizontal. It's actually going to be a slant asymptote. And now I'm going to finally show you how to find a slant asymptote. Number 11, if they actually want you to find a slant asymptote, and the directions are a little different here, so I'm just going to write them out. Find the slant asymptote. Okay, what you basically do is you divide. You actually divide this out. I'm going to use synthetic division because it's faster. So I'm going to use 2, and I'm going to divide into 2, negative 5, and 7. So 2, 4, negative 1, negative 2, and 5. Okay, that means that I divided a first degree into a second degree. So this is actually 2x minus 1. We disregard any remainders in this instance, and we simply say that y equals 2x minus 1 is our slant asymptote. It's basically a diagonal line like this across our graph that our graph doesn't cross, doesn't touch. Here's an example of what you might see as a slant asymptote. You can see the graph never crosses that diagonal line.